Hello everyone, and today we will be having our lecture number 17 for linear algebra, and we will specifically go over two examples that we pick from MIT recitations um, regarding solving system of linear equations. Till now, we have looked into many ways uh, of solving this linear system of equation, which is AX equal to B. But today we will like to look in a summarized manner what we mean when we say we wanted to solve AX equal to B. And we are saying that there are couple of linear uh, system of equations, couple of linear equations, and they are belonging to one system. They're giving us various clues towards the working of that physical system. Um, or we can say that there are evidences regarding that one particular physical system. And we have to solve them simultaneously. We have to solve them as a system of linear equations. For this, we will develop AX equal to B. And today we'll see in a summarized manner how we can reach and tackle that problem. There will be many things that we will discuss regarding the spaces, column space, null space, left null space, and row space. So let's start with this particular example. In this example, we have three equations. The first equation, linear equation, is x minus 2y minus 2z equal to b1. Now, b1 is a constant. It is some number. But right now, we don't want to take uh, the name of that number, or we don't want to pick that number. So we represent it with the parameters b1. Then we have 2x minus 5y minus 4z equal to b2. So now b2 is also a number which we can pick from the real line. It's a real number, okay? But for the time being, we think of it as a parameter. Then we have a third equation, 4x minus 9y minus 8z equal to b3. So now this particular equation also contains a parameter which is b3. So in this system of equation, we have three parameters, b1, b2, b3. Based on these parameters, our solution will change. Now, what is the meaning of a solution? The meaning of a solution is it is the values of x, y, and z, which will be able to solve all the equations simultaneously. So it means if I have found that solution, then that solution should satisfy the left-hand side and right-hand side of the equation 1. That solution should be able to satisfy the second equation. It means for the second equation also, the left-hand side should be equal to the right-hand side. And also, it should be able to solve the third equation. And when I plug that solution, which I have already tested for equation 1, 2, that particular solution, when I test it for equation number 3, it should also give me left-hand side equal to right-hand side. So how to approach a solution for this system of linear equation? The first thing that we do is we make an augmented matrix. We put them in the matrix notation, okay? And so let's move forward and write it. So here is the augmented matrix um, for AX equal to B. Now, how we make the augmented matrix for AX equal to B is that we usually take the coefficients on the left hand side. So you see here, this 1 came from the coefficient of X, this minus 2 came from the coefficient of Y, this minus 2 came from the coefficient of Z. Similarly, this minus 5 came from the coefficient of Y in the second equation. This minus 8 comes from the coefficient of Z in the last equation. And then we skip those X, Y, Z, which is X vector, and we just put this dotted bar just to show that we are going to cross this equal sign and we are going to the other side of the equal sign, and where we find these three parameters b1, b2, b3. So we now write this whole thing as an augmented matrix. And we move forward and try to, now we will reduce it. We will use Gaussian elimination to basically convert this left hand side, this coefficient matrix which we have right now, a1 minus 2 minus 2, on the second line 2 minus 5 minus 4, then 4 minus 9 minus 8. This is a coefficient matrix. We would like to use some row operations, and we will like to convert it into an upper triangular matrix. So when we say upper triangular matrix, we means that across the diagonal, the upper side of the diagonal, we can tolerate some non-zero entries, but on the lower part of this diagonal, we will like to have zeros. So this is called an upper triangular matrix. So a triangle is created by just drawing a line across the diagonal, and then most probably everything below the this diagonal is converted into zero. Now, in order to do this, in order to convert it, we will use some row operations. So we will start with the first row of this augmented matrix. Then the first non-zero entry is considered to be the pivot. So this one is the pivot. Now we will use this pivot entry, and we will try to get rid of these two. And at the same time, we'll try to get rid of 4. So we will find a multiplier of this one. So here I know that if I multiply with minus 2 this row and add it to this one, then I will get rid of this. But this minus 2 will not only multiply with this entry, this minus 2 will multiply with all the entries in this row till B1. And then the whole row is multiplied with minus 2 and added to this second row. Similarly, in order to get rid of 4, I decided to multiply minus 4 with the first row and add to this one. So once I decide the number, the decision is made based on this entry, which we call pivot entry, and the one here. But once the multiplier is decided, then it has to be multiplied with the whole row, and the whole row after multiplication is added to third row. So the whole third row is affected. So in this whole operation, only the first row is not affected, but the second and third row is completely affected. So let us say we did this operation, as you can see with the arrows, and we end up with something like this. Now, if you see here very clearly, these two zeros are created now, okay, and the whole row 2 and row 3 is changed. Only the row 1 is unchanged. And now here you can see these numbers, these are also being added. So now our pivot, second pivot is this one, minus 1, the one which is in the second row. So this entry where I'm putting my cursor around, so this particular um, entry is my pivot. So I will use this minus 1 and I will get rid of this one. So I know that if I multiply this row with minus 1 and negative 1 and add to this one, definitely this minus 1 is gone. In order to do this, I will take this minus 1 multiplied with the whole second row and add to third one. So in this case, second row will be unaffected. Only the third row will be changed. So if I do this operation, you can see very clearly now that I got all zeros, and on the other side of this dotted line, I got minus 2 B1 minus B2 plus B3. So now the situation is very clear. Now this whole coefficient matrix is now converted into upper triangular matrix. The only thing which is surprising is that if you look at the third row, all the entries are 0 in the coefficient matrix. Whereas in the augmented matrix, if I look on the other side of this dotted line, I got these numbers. So now on this side, so if I convert this matrix entry into our equation, as you remember, in the beginning we have equations and we move to matrix notation. And we did operation on matrices, row operation using Gaussian elimination method. However, keep in mind that at any instant of these operations, we have every right to go back to the equations, and we can interpret that matrix that we get as a result of the row operation as a system of linear equations. So here again, there are three system of linear equations, and we can convert this particular augmented matrix back to equations. But these equations will not be the same as we started, because now we have done some operation. So if you look into the very last row, and if I convert this very last row into a an equation, a linear equation, then it will become 0x plus 0y plus 0z equal to minus 2b1 minus b2 plus b3. Now here the strange situation is. So in the last equation tells me that I have zeros on the left, but I have the entry which is a number which is minus 2b1 minus b2 plus b3. So if I write it down, I think I can. So the last equation tells me that I have 0 equal to minus 2b1 minus b2 plus b3. Now this tells me that if my left hand side is 0, my right hand side also need to be 0, because if this right hand side is non-zero, then I have something which is called inconsistent system. I have inconsistency. And if I have inconsistency, it means that there is no solution for this system of linear equations. So here I see it exactly like this. So, but keep in mind, this 0 is not actually a 0. Actually, it came from this whole operation, which was 0 times this x plus then 0 times this y plus this 0 times z. Now this whole thing, since their coefficient is 0, now keep in mind these variables x, y, and z are not 0. What we are saying is that their coefficients are 0. So once their coefficients are 0, no matter what x and y and z values are chosen, this will ultimately end up into 0. So our left-hand side is completely 0, whereas the right-hand side, we have these parameters. Now, if these all minus 2b1 minus b2 plus b3 is not 0, then we get an inconsistency, because on the left-hand side, we have 0, but on the right, we don't have 0. So then definitely this ax equal to b has no solution. Okay, it means the planes are the equations, if I try to geometrically interpret them, then it will mean that it is three planes. These are three planes in R3, and then these three planes are not intersecting at the same point. They don't have a single point which is common among them. Okay. Or in other words, I can say that one of the plane is parallel to the other one. That could be a condition where there is no solution. Okay, so once you have a one plane which is parallel to other two planes, then there is a chance that you have no solution. Anyway, so now what we assume right now, in order to proceed in this particular problem, we will assume that this minus 2b1 minus b2 plus b3, this particular number that we get is 0. Once we see that this is 0, then the last equation will become consistent, 0 equal to 0. And once they both are 0, then we can proceed. But keep in mind, then in this case, when 0 is equal to 0, you will get many solutions. Okay, so now the unique solution situation is gone. One way to look at why this solution is gone is the reason that you only have two pivots. Pivot in the first column, you have pivot in the second column, but you don't have any pivot in the third column. You are supposed to have some non-zero entry here, but what we see here is zero, so it means there is no pivot. So if you don't have a third pivot, it means that you don't have a unique solution. Or in some way, you can say that there is no A inverse. A inverse basically is a coefficient matrix that has to be invertible. So you have a square matrix A, but it is not invertible just because you don't have three pivots. Okay. So let's proceed and assume that minus 2b1 minus b2 plus b3 is 0. So if we assume this, and now I will like to first remove those my entries that I just put in, because okay, now I will just remove those. Okay, good. Now I am in a situation where I can say that if minus 2b1 minus b2 plus b3 is not 0, then the system becomes inconsistent, no solution. So I can declare no solution. However, if minus 2b1 minus b2 plus b3 is 0, then there is a solution. Yeah, and that solution we are going to find. But keep in mind, it will not be a unique solution. It will be many solution situation. Okay, good. So in order to find this many solution situation, we will use -1 and also remove this -2. Once we are doing this, this become what we call reduced echelon form. So reduced echelon form we will find. Till now we were doing this Gaussian elimination to get an upper triangular matrix, and now we will move forward and do this RREF, which is reduced row echelon form. In this case, we will like to have a pivot, and then the entry above pivot and below should be 0. But below is already 0 because it's an upper triangular matrix that we got from Gaussian elimination. So now we will use this row and we'll try to eliminate this one. So we'll use this -1 to eliminate this one. So we will multiply this -1 with -2. This will make him +2. And when we add this +2 to -2, this entry will be 0. So we have to do this operation with this whole row and add it to upper row. So if we go along this procedure, so what we will get will be this one, 1, 0. Now you got 0 here. You see, this is the operation we did, which is called reduced row echelon form. So now we use this -1 and get rid of -2. And once we get rid of this also in some way change this side, because this whole row was multiplied with -2 and added to this one. So if we do this, we will get 1, 0, -2. Now, in order to get rid of this -1, we multiply this row with also with -1. So if I do this, this will become this minus will be gone, so it's become 2b1 minus b2. So you can see this now. Now here, this is now in reduced echelon form. So if you look into this first column, it contains pivot. So this column belongs to X. If you look at the second column, it also contains this pivot. So it is called Y column. We have X column, we have Y column. However, here we don't have, this is Z column. So in this Z column, there is no pivot. If you don't have a pivot in any column, that variable is declared as a free variable. So now we have X, Y, which are two variables, but we have a Z as a free variable. So in case of free variable, we need to understand that our solution will consist of particular solution and then a C times, okay, a variable times, okay, a C times the spatial solution. So for particular solution is for the system Ax equal to B. So particular solution is Ax equal to B, where we put the free variable equal to 0. So if you put the free variable, so in our case, the free variable is Z. Once we put this free variable equal to 0, we get, so now if I put the free variable 0, this will become x equal to 5b1 minus 2b2, because this minus 2 multiply with z, and z is also 0. Now the second line, the second row will give us the equation y will be equal to 2b1 minus b2. And the third one is 0 equal to 0, because we have assumed that this whole number minus 2b1 minus b2 plus b3 was 0, because that's how we proceeded. Otherwise, we have no solution condition. Okay, so now we have this solution here. Okay, good. So now we have, this is our particular solution. We write it x with subscript p. Now let's go for spatial solution. Spatial solution belongs to a homogeneous system of equations. So we will replace this b with 0. So now we have Ax equal to 0. So it's kind of we are trying to find null space. So we have a null space here, Ax equal to 0. So we are trying to find all the vectors, once they multiplied with A, they goes to 0. So in order to find this one, okay, I will use RREF, but on this side, we will be using everybody 0. So if we use everybody 0, what you find out is, now in this case, z is 1. Because keep in mind, z is a free variable. Last time when we were trying to find, just a while ago, we were trying to find particular solution, we put z equal to 0. And now we'll put z equal to 1 to find the spatial solution. So, but we can do this because z is a free variable. We can give any value to z. So now this is a special variable. And now if you give z equal to 1, this will become x minus 2z equal to 5b1 minus 2b2. So if the z is 1, so this become x, then this become minus 1. Okay, so now our solution will become equal to, but keep in mind, these b's are not here because we have ax equal to 0. So the spatial solution basically put the right hand side equal to 0. So these all are zeros. So this is 0. So it's x minus 2 times z, and z is already 1. So x minus 1 equal to 0. So it means x is equal to 1. So we will put x equal to, so now you see that this minus 2 when goes to the other side become 2. And now if you look into the next row, this is y, and y equal to 0, because you keep in mind this is ax equal to 0. So this side is all zeros. And now you have the lower part and where you need z. Now we already assume z is 1. So we have now one particular solution and many spatial solutions. So once the spatial solutions, which is a complete set, is added to this particular solution, that's how we get solution to ax equal to b. And I will tell you a small interpretation of it. You can think of it that this ax equal to 0 is a null space. So it's not one solution, it's many solutions, because we can think of it as c times this spatial solution xs. So if you look, this is c times xs. So it means there are, and what c is? C is some number that you have chosen from a real line. So there are as many solutions as there are real numbers. So this is a very big set. This is not one solution. This is a very big family of solution in which you can pick any c from a real line and you multiply with xy, which will give you. So this is a So think of it as a space. And which type of space this is? This is a null space. So this, and in this case, it is, this null space actually is a subspace of R to the power 3, because there are 3 components, X, Y, and Z. But since it is one point, it means that it is making one line, because the tip of this vector is at coordinates 2, 0, 1, but the tail is at 0. So if you look into this, this is a vector. And now if I multiply this vector by C, I can elongate it and I can reduce it, but I cannot change the direction. So it means that the whole null space is geometrically a line that passes through this arrow, this vector, okay? And once we add this XP, now XP is only one arrow. These are millions of arrows, but these all arrows are lying on the line. And this is another arrow which does not lie on this line, okay? Because in this case, Z was 0, here Z is 1. So it means that this vector cannot be part of this particular null space. So now you have a line as a null space and you have this vector X. So it means that this is an orthogonal vector to this null space. And now this particular vector will lift this line. So this line was before, so at 0, but now it is lifted upward. So if I want to draw it like this, it will be something, let me draw the coordinates. So okay, so it was before, it was this line that goes through the origin, let's assume. And now because of XP, it is elevated in this direction. Can you see this now? And now you got this line. This is the line which is X, because this line contains this line, which is X dot or multiplied with XS. Okay, this is this line. Okay, and this XP is just one arrow, which is represented by this particular arrow. And because of this, you got X. Now, what is X? X is a line which does not pass through the origin. So here is the X. X is also a line, but this line is elevated by the amount of XP away from the origin. So this null space is lifted. So this is a lifted null space, okay? And this is the solution to AX equal to B, okay? So let's hope that you understand that example, because I felt that this example is a very good representation of what can happen with a system of linear equation. And since we have put some parameters, so it was really nice to see once when we can have no solution situation and when we can have many solutions, and how to represent many solution scenario, how to tell, and you can see very clearly the many solution scenario is because there is a C, and this C actually belongs to the real line. So this is a complete whole space of solution. This is not just one solution. This is a whole space of solution. And then this space of solution is added with this vector and is lifted from the origin. Okay. So I hope that you understand and comprehend this, because I also took a time to comprehend it, but believe me, this will enhance your capabilities of understanding the solutions to the system of linear equations. So good luck. If you have any questions related to this example, you can ask in the comments of YouTube, and you can also send me your questions on Google Class. So thank you very much, and I will see you next time. Take care, and bye-bye.